Welcome back. Only one thing is happening in this video, and that's an explanation of the decibel scale for sound levels. Although, in order to really take a careful look at how the scale works, we need to review logarithms. Some of you are totally hip to logarithms. Others of you could use a lot of help. So those of you in the first category will probably be very irritated with me by the end of this lecture video, because I'm going to review them in detail. Now, some of you maybe feel like logarithms are not totally intuitive. You may have struggled with them back in Algebra 2 or pre-calculus, whenever you learned about them. But I think they're very natural. In particular, the natural logarithm is quite natural, because a lot of the language that we use in everyday life is implicitly logarithmic. Here's an example. You hear people talk about 6-figure salaries, 7-figure salaries. Well, if I understand this correctly, a 6-figure salary is one over $100,000. Now, in science, when we use scientific notation, powers 10 to the 6th would actually be a million. But here we're counting not just the zeros, but the 1 here as well. So you could write this as $0.1 times 10 to the 6th. And then a 7-figure salary in the millions would be something like 0.1 times 10 to the 7th. So we're really describing that salary using a power of 10, which is actually logarithmic, because it's easier to just say 6 than it is to say 100,000. And it's easier to say 7 than 1 million or 1,000,000. So when we use the power of 10 as a shorthand, we're actually talking about the log base 10, as you'll see in a moment. Let's take another example. I just looked up the US debt. Wasn't it just like 14 trillion last week? I can't keep up with this number. We've got a lot of people in the world now who are billionaires, multi-billionaires. Something's off about this picture. Can't quite put my laser pointer on it. Wow, 90 billion. I'd take that. On a smaller scale, just a couple years ago, evidently our school had a $14 million bond measure for fixing up the D building. Did that actually happen? I didn't realize our building was fixed. I must have not been paying attention. So let's look at these words: trillion, billion, million. I've thought about this for a while. What's up with million? Because mil means 1,000. Well, I guess a million means 1,000,000. So if you count to 1,000, 1,000 times, you've counted to a million. 10 to the third we know is 1,000. So here it is, 1,000 thousands. So we've got 1,000 to the first power. Now the number 1 billion has an extra 3 zeros in it. So that's like 10 to the third squared times 1,000. And we know that the prefix by means 2. So it's the second power of 1,000 times 1,000. Trillion, the prefix tri we're all familiar with. So that's the third power of 1,000 times 1,000. So again, when we use these words, trillion, billion, million, rather than say, the national debt is 26,000,000,000,000,000,000, which is really inconvenient. We use the word trillion, which is in a way describing a power of 1,000. It's the third power of 1,000 times 1,000. Okay, so what does it mean to take the log base 10 of 10 to the third? I'll try to just phrase this in a couple different ways. To what power must you raise the number 10 in order to get 10 to the third? Well, the answer is in the question. Hopefully, I'm picking the easiest possible example here. I could also phrase it this way: 10 to what power is 10 to the third? That makes it even more obvious, right? 10 to what power is 10 to the third? Of course, 10 to the third power is 10 to the third. You could even say, what's the power of 10 that gives 10 to the third? Well, that's 3, of course. So what's the power of 10 that gives 10 to the 9th? That would be 9. What's the power of 10 that gives 10 to the negative 2? Okay, you're probably irritated at this point. This one's not so obvious. 10 to the 0, you all remember, is 1. So 10 to what power is 10 to the 0? Well, it's the answer is still in the question. It's 0. Now, if I had written these numbers in decimal form, not in exponential form, then I suppose it's not quite as obvious. 10 to what power is 1,000? Well, we all know that every time you multiply by 10, you pick up another 0. You can just count zeros, right? 10 to what power is equal to a billion? There's 9 zeros, hence 10 to the 9th power. Okay, this one, I guess, is slightly less obvious. 0.01, that's the same as 1/100th, which is 1 over 10 squared. So you still have the power of 2, but because you're dividing by 10 squared, we use a negative exponent. This one you should just memorize. In a moment, we'll look at the fact that the log base anything of 1 is 0. So even if I changed the base here to 2, 3, 50, root 17, it doesn't matter what the base is. The log of 1 is 0. You should memorize that. The log of 1 is 0, regardless of the base that you're using. Let's switch base then. The log base 2 of 8. Well, what's the power of 2 that gives 8? In other words, what power must you raise 2 to get, that's awkward, to what power must you raise 2 in order to get the number 8? Well, 2 times 2 times 2 is 8. So 2 cubed is 8. The log base 8, excuse me, the log base 2 of 8 is 3. What is the power of 2 that gives the number 32? Well, 2 to the 5th power, you can do that in your head if you don't have that memorized, is 32. You know, we all learn times tables. Most of us learn times tables in grade school. I think 6th grade. By then, a lot of people have memorized their times tables up to like 12 times 12. I don't see a reason why we shouldn't learn some of the basic logarithms around that age, or maybe junior high. Just kind of memorize them because they're really useful. Like, what's the log base 2 of 64? Well, 2 to the 6th power is 64. So the log base 2 of 64 would be 6. Okay, what about this one? Well, 16 is the same as 2 to the 4th, but since it's in the denominator, we need that minus sign. This is just some review, some practice. Did this require any thought? Remember, the log of 1 in any base is 0. Some special notation. If the base of your logarithm is this very special number e, I almost called it Euler's constant, but that is not Euler's constant. I think that means something else. But the letter e does come from the mathematician named Euler. We just call that ln of x, the natural log. Maybe you're wondering, sorry, I keep having to pause to cough. It's that post-COVID cough, no joke. I think it's in French. Like, I'm not even going to attempt to pronounce it in French, but it's natural log in French. Same thing. You could write log base e or ln, same thing. Okay, what is the log base e of e? And remember, e is something like 2.72, I believe. If you round to the nearest hundredth digit, I believe it's 2.72. E to what power equals e? Well, of course, e to the 1st power is e. So the logarithm of e, base e, is 1. We can just write it that way. I guess that's worth memorizing. ln of e is 1. What about this one? The square root of e. Well, isn't that the same as e to the 1/2 power? So e, when we read this, natural log of root e, we're asking ourselves, since the base is e, e to what power equals e to the 1/2? Well, of course, that's 1/2. The answer is in the question. Here's a fun one, because you're probably rolling your eyes at some of these. They're so easy. So fine, figure this one out. What's the natural log of -1 since you're so smart? Maybe you're thinking there is no real number for which you can calculate the no, there is no real number that is the natural log of -1. In other words, e to what number equals -1? I wish I had a graph up here of e to the -x, and you would see that the output of e to the -x, it's got this shape, right? It's that exponential decay. The output of that function is always a real number. You can't plug any number in and get Hang on a second. Am I saying that right? No, let me correct that statement. If this is the x-axis, when you graph e to the negative x, you have a function that's always positive, right? The output of that function, e to the negative x, is always positive. So there's no, what number could you plug in and get -1? Well, you're right. There's no real number, but it is possible to get to plug in an imaginary number and get -1. We don't need that in this class. Although I will point out a lot of the stuff we do later this semester, when we talk about diffraction, interference, and maybe when we talk about wave functions for particles, matter waves at the end of the semester, a lot of those ideas can be expressed more easily using complex numbers, which of course have a real part and an imaginary part. So a lot of you are going to use imaginary numbers later in your academic careers. Like if you study electrical engineering, you'll see a lot of use of complex functions. Moving on. Here's a useful property of log, or just logs, I should say. Suppose you want to know the log of some number in the base 11. There's no button on your calculator for log base 11. There is, however, most likely a button on your calculator for log base e and log base 10. So if you'd like to know the log of a number in some funky base like 11, here's the rule. I'll just say it in words. It's not easy to memorize in words. It's also not easy to memorize in symbols. For me personally, the only way to remember this is to use it a few times. It's almost like muscle memory on the calculator. If you want the log in some weird base, you first calculate the log of x in a traditional base and then divide by the log of the new funky base in that traditional base. That's a mouthful. Why don't we just do an example? Suppose we'd like the log base 10 of 1,000. And I chose this one, not because 10 is a funky number, but because we can check this easily in our heads. Suppose you had a calculator that only had the natural log button, not log base 10. Well, in order to calculate the log base 10 of 1,000, you could first calculate the log base e of 1,000, because I'm supposing that you have that button on your calculator, and then divide by the log of the new base using the old base. Does that make sense? So both of these logs are done base e because presumably you have that on your calculator. Let's check. Well, that would be the ln of 1,000 divided by the ln of 10. I use my calculator to get these numbers. And sure enough, when we do the division, we get 3, which is the answer we could see from the beginning. Obviously, the log base 10 of 1,000 is 3. So this rule works. Let's go back to Desmos. Have I talked about Desmos yet? Have I extolled the virtues of this free graphing calculator? Of course I have. I'm turning into a big Desmos dweeb. It's kind of like a professor I knew years ago at Cal State Northridge, who shall remain nameless. He was really excited about his TI. It wasn't an 85. It was a much bigger, clunkier calculator. Everything it did, you could do with an app on your phone now. But if you ran into this man in the hall, he would show you his TI 200 or whatever and talk about it. It was very amusing. Great teacher, by the way. Okay, now that we know how to express the log base anything in terms of the log base a known number or with the known base, suppose, I'd like to investigate the behavior of the logarithmic plot as you tweak the base. So I'm going to make the base a parameter. So y equals, actually, I don't need the y equals. I'll just type log. Okay, fine. Maybe this makes it a little clearer. Y equals log of x divided by log of a. So if you apply the rule that I just discussed, what I'm actually doing here is calculating or graphing the log base a of x. When I just type log, I think that Desmos is assuming that I mean log base 10. It actually depends which program or calculator you're using. Some books, programs, calculators use log to mean log base 10. Others default to log base e. I'm not really sure which is which here. It doesn't matter because I'm taking the log in a known base of x and dividing by the log in the known base of some new base. So what I really have here is the log base a of x, and I've made a parameter. Okay, so presently the value of a is 1. Now what's the log of 1? Remember, the log base anything of 1 is 0. So I'm really dividing by 0, which is undefined, and that's why we don't see anything on the graph here. As soon as I drag the slider to the right, we actually see something. So how about I put the slider at a equals 2? What I'm really graphing right now is the log base 2 of x. So what's the log of 6? Evidently, it's, let's see here. Since this is 2 and this is 4, right here would be 3. So it's something like 3.5. Evidently, the log base 2 of 6 is around 3.5. Let's check something. Hopefully you can do this in your head. What's the log base 2 of 2? 2 to what power equals 2? Well, of course, the log base 2 of 2 is 1, because 2 to the first power is 2. And sure enough, if we go to the x coordinate 2, the height of the function is 1. The log base 2 of 2 is 1. So you can always, when you're looking at a logarithmic graph, you can always figure out what the base is by looking at the horizontal line y equals 1 and looking at where it intercepts. For instance, if we go change the base to 5, I could just type in the number 5. I got it. So what's the log base 5 of 5? Well, 5 to the first power is 5. So if we go to x equals 5, the logarithm base 5 of 5 is in fact 1. All right, so look at where the horizontal line y equals 1 intercepts the graph, and the x coordinate at that interception point is the base of your function. And you'll notice, excuse me, as I drag the slider around, oops, the overall shape of the logarithmic function doesn't change a whole lot. Right? Of course, something weird is happening when I go to a negative base. I'd have to think about that. But do you see the 1 point on this graph that does not change as you change the graph or change the base? So I'm sliding the base around. There's 1 point that doesn't change, and that, of course, is the point 1, 0. That goes back to the fact that I mentioned a moment ago. It doesn't matter what the base is. The log base anything of 1 is 0. Let's say the base of your logarithm is 13. 13 to what power equals 1? 13 to the 0 power equals 1. So every plot of the logarithmic function, regardless of the base, will pass through the point 1, 0, which is a useful fact when you need to go sketch or hand draw the logarithmic function. Now, a couple behaviors of this graph that you should observe are, number one, the fact that the logarithmic function climbs very slowly. It does not rise rapidly. In fact, I can scroll all the way out to enormous number, well, big numbers like 1,000, 1,500, and the graph looks almost flat from a distance. It takes a long time for the log function to climb appreciably. It does continue to climb. Like if you go out far enough, you can make the log function go as high as you want, but it takes a long time, which makes it useful for a lot of purposes. You'll also notice that as we approach 0, it dives down to what looks like negative infinity. The y-axis appears to be a vertical asymptote. So we'll confirm that behavior in just a moment. And you'll also notice that there is no negative output. Actually, let me back up. I'm really talking about the domain. Yeah, that was incorrect, what I just said. You can get negative numbers out of the log function. Notice that for every input, meaning every x value that you plug in between 0 and 1, you get negative output. And that's true regardless of the base. If I scoot the base around, That fact does not change. So if you plug in a number between 0 and 1 to the natural log function or the log base 10 function, you will get negative numbers out. However, the observation I was trying to make is that the domain appears to be restricted to values of x greater than 0. If you plug in a number like negative 20, you don't seem to get anything out of the natural log function. So a few slides back, I asked you what the natural log of negative 1 was. And I'm sure you were stumped for a moment. It's the same thing, right? The function does not appear to be defined for input values on the negative axis. However, you can get meaningful numbers out of the natural log function when you plug in negative numbers, but then you have to expand your range to the complex plane. All right, moving on. So let's confirm the behavior I mentioned about the vertical axis being an asymptote. I should say the y-axis being a vertical asymptote for any base logarithmic function. Now, this statement here is just the sort of thing that an uncouth physicist would say. In calculus, if you find that the limit of this function as x goes to 0 is infinity, you wouldn't actually say that. You wouldn't say that infinity is the limit. You would say the limit's undefined or doesn't exist. Yeah, the limit does not exist. But I'm being sloppy and just saying as x goes to 0 from the right side, from the positive side, the output of the function shoots down to negative infinity. Let's just confirm that with the particular base. How about the familiar a equals 10? So what is the log base 10 of 0.001, which is a fairly small number. Now 0.001 is 1,000th, which is 1 over 1,000. In other words, 1 over 10 to the third. So there's the logarithm. Now this is a negative number. Remember I said that when you plug in numbers between 0 and 1, you get negative output from the logarithm function, but it's certainly not a very large negative number. It's not close to infinity, so to speak. So let's keep getting smaller. What about the log base 10 of 1/1,000,000th, or 1 over 10 to the 6th? It's a negative number that's larger in absolute value. And then we'll skip over a few powers of 10 and just go to something really small like, how would I say this number in decimal form? I'd say 0.00000. I'd say it almost 999 zeros and then a 1. And evidently the logarithm of that number, 0.00000 1,000 times until you get to the digit 1, that is just negative 1,000. So the logarithmic function is diving down towards negative infinity, but it's still going to take a while to get there. So I didn't put this in a slide, but what would be the log of 0? We're getting close to 0 here, but you can't really take the log of 0 and get a real number out. What you get is, I guess, negative infinity. Okay, let's talk a bit about the inverse of a logarithmic function. And before I do that, I suppose we should just briefly review the definition of an inverse function. In this context, talking about the inverse of a logarithmic function, sometimes it's called an antilog. It's a bit like cosine and arc cosine. Sometimes people say arc cosine instead of inverse cosine. Well, here we can say antilog for the inverse of a logarithmic function. So you may recall that if we're talking about a function f of x, the so-called inverse function f inverse, so that's how you read this. You don't say f to the negative 1. F to the negative 1 would be 1 over f, and that's not what an inverse function is. So that notation can be a little confusing. If you're wondering why they use that notation, it's because 3 times 3 to the negative 1, for instance, is 1, right? 3 to the negative 1 is 1/3. So 3 times 3 to the negative 1 is 1. In other words, 3 and 1/3 are multiplicative inverses, because when you multiply them together, you just get the identity, 1. That's where this notation comes from. But make sure you understand, this does not mean f to the negative 1. Excuse me. If you know the inverse function and you call it f inverse, by definition, if you plug x into the function f of x, and then you take that output and plug it into the inverse function, that's the outer parentheses here, you just get back the number that you started with. And the order doesn't matter. You could also plug X first into F inverse, take the output of that, and then plug it into F, and you would still get back the number you started with. So the order is immaterial. Well, to be honest, that kind of depends on whether you're talking about what's called a surjective or injective or bijective function, but that's above our pay grade here. Here's an example. Let's say your function is a simple line. So in order to compute f of x, you just take the number x, you multiply by 3, and then subtract 4. What would be the inverse of that? Like, how would you undo that to get back to x? Well, if you first multiplied by 3 and then subtracted 4 from your starting number, in order to undo that, you could first add 4. That cancels the effect of subtracting 4. And then at the end, divide by 3 to undo the operation of multiplying by 3. In other words, F inverse would look like this. First, take your number, add 4, and divide by 3. So let's check. What's F inverse of f of 5? If we first plug the number 5 into the function f, and then take the output from f and plug it into F inverse, those two functions should undo each other and get us right back to the number 5. So first we'll evaluate the inside. What's f of 5? Well, we take the number 5, we plug it in here. 3 times 5 is 15. 15 minus 4 gives us 11. So now we take the number 11, which is the output of f, and we make that the input for F inverse. What is F inverse of 11? Well, you take 11, you add 4 to give 15 divided by 3, and that gets you back to 5. So yes, F inverse of f of 5 does give you 5. Those are the correct, or that's the correct inverse function that I used. In order to guide us towards the inverse function of a logarithmic function, let's look at this example. First, I've calculated, or I'm looking at the log base 10 of 10,000, and then whatever that number is, the log base 10 of 10,000, I want to raise 10 to that power. So I've got two operations here. I'm taking the log base 10 of a number, and then I'm raising 10 to that second number as its power. Well, log base 10 of 10,000, hopefully this is obvious, is just 4. You can count the zeros. 10 to the 4th power is 10,000. So now we take 10 and raise it to that power, and we get, of course, 10,000. So look what just happened here. We did something to the number 10,000. Then we did something to that, and we get back 10,000. Evidently, taking the log base 10 of a number and then raising 10 to that power, those two operations undo each other. And so perhaps we've discovered already the inverse function for taking the log base 10. And it doesn't have to be the number 4 here. That logic would apply for any number that you plug in to the power of 10 right here. So what do you think? If I take the log base 10 of 87.16691, and then whatever that number is, I raise 10 to that number, what do you think I'll get? You could check it on your calculator, or you could just recognize that these two functions undo each other. Taking the log base 10 and then the anti-log meaning raise 10 to that number, those two operations undo each other, and of course, you just get the same number right back. We'll just state that as a rule then, that 10 to the log base 10 of x is just x. Taking the log and then the anti-log, those two operations undo each other. Put another way, if the function f is defined as the log base a of x, then the inverse function would be a to the x. So here's the log base a, here's the anti-log, I suppose you could say, and vice versa. If the function is the anti-log, then the inverse function is the log. I think you know all this stuff. Sure, I'm beating a dead horse here, but that's just to make sure we're all on the same page, or to give you a brief review before we use logs for calculating decibel sound levels. So let's do a check. Is the log base 2 of 2 to the 3rd equal to 3? Well, if you just use the rule, you can see that should be true, but as a check, 2 to the 3rd is 8. What's the log base 2 of 8? 2 to what power equals 8? Yes, of course, that's 3. Now we get to the applications of logarithms to sound waves and the intensity of those waves. That's the whole point here. So it's an observational or experimental fact that if two people are chatting at a normal volume, if you're standing or sitting 1 meter away from the person talking, the intensity of the sound waves from that person's voice, which impinge on your eardrum, have an intensity of about 1,000th of a watt per square meter. And you could call that 1 milliwatt per square meter. Another typical sound, if you're outside, the very faint rustling of leaves several feet away. That's a much quieter sound, I think we can agree, unless there's a hurricane going on. And the sound intensity is so much less, it's a number as small as 10 to the negative 10th, so less than a billionth of a watt per square meter. And you can look these numbers up in tables. How about Ted Nugent on stage around 1979? I hear those were extremely loud concerts. It could be a sound wave, if you're near the stage, as intense as 5 watts per square meter. And now you're getting close to an intensity that could really damage your eardrum or worse. Or I should say damage your hearing or worse. I mean, what's worse than damaging your eardrum? I can't imagine a sound wave so loud that it like killed you. That doesn't seem possible, at least not here on planet Earth. So look at the extraordinary range of these numbers from as small as 10 to the negative 10th all the way up to 5, which makes it very awkward to assign values to other sounds that are intermediate. For instance, what if you had to guess based on the fact that this intensity is rustling leaves and this intensity is a person speaking a couple feet from you? What do you think the intensity of sound waves emitted by water flowing in a creek would be? So I don't know, you're 20 feet away from a small creek, you hear the water, a babbling brook, let's say. Where is that number in between 10 to the negative 10th and 10 to the negative 3rd? Because I hope it's obvious that should be louder than rustling leaves, but probably not as loud as a person speaking a few feet from you. So try to interpolate, right? Where is that number? Is it closer to 10 to the negative 10th or closer to 10 to the negative 3rd? It's a huge range. I have no idea. It seems like an awkward question because it is awkward as a human with human senses, human audition. That's the fancy word for your sense of hearing. It's awkward for us to use the SI units of intensity to describe how loud something is, because our perception is really logarithmic in nature. So enter the decibel scale for making it more convenient to describe the intensity of a sound. So here's the distinction we'll make. Instead of calling it merely sound intensity, follow that up with the word level. Sound level implies that you're using the decibel scale. If you just say intensity, most likely you're referring to the SI units of the actual physical quantity intensity in watts per square meter. The level will be something different. So there's a number of steps here for computing the decibel level. I guess sound intensity level is interchangeable with decibel level. First, you need what's called a reference intensity. This is an extremely quiet sound that many people can hear. It's at like the threshold of hearing. Any quieter, and you just wouldn't be able to perceive it. So that value is chosen to be 10 to the negative 12th, or 1/trillionth of a watt per square meter. And of course, that number is somewhat arbitrary. Why is it convenient? Because it's a nice, clean power of 10. You know, for some people, maybe they can actually detect intensities as low as 0.5 times 10 to the negative 12th. And some people are a little more deaf and can only hear sounds as quiet as 2/trillionths of a watts per square meter. So this number is convenient. Then what you do, you take the intensity you're actually talking about, be it rustling leaves or a person speaking, and you compare that to this reference intensity. You take the ratio. Next, you take the log base 10 of that ratio. And here's where the convenience comes in, because this ratio could be an extraordinarily large or small number. For instance, the Ted Nugent concert compared to the rustling leaves, what was that? 5 watts compared to the 10 to the negative 10th. Let's just call that 10 to the 10th or 10 billion. The Ted Nugent concert involves sound waves that are something like 10 billion times as intense as the sound waves coming off of rustling leaves. That's a very large, unwieldy number. How do you turn a big, clumsy number into a number that's easy to pronounce and easy to conceptualize? You just take the log. The log function humbles the large numbers. It brings them all down to scale, no matter how big they are. I mean, well, I shouldn't say no matter how big, but in science and even math, you don't often encounter numbers that can't be tamed by the logarithmic function. You saw how slowly that graph crept up, right? In Desmos, even when you zoom out and you look at the logarithm of like 1,000, a million, that graph is still almost flat when you zoom out. Okay, the last thing you do, and you'll see why, is just to scale that up by a factor of 10. That makes the final scale just a little more convenient. For whatever reason, as people, we like to rate things on scales of 1 to 100. We like to talk about percentages. Yeah, a lot of things we also do on a scale of 1 to 10, but rating things from 1 to 100 gives you a little bit more resolution. That's why, of course, a lot of instructors like to grade your exams on a scale of 1 to 100, so they can be a little more meaningful. Like, what if I don't want to give you a 7 because it's too generous, and I don't want to give you a 6 because it seems a little mean, and that would hurt your self-esteem on a scale of 1 to 10. So if we make the scale 1 to 100, I could give you a 66, let's say. Okay, let's look at an example. And by the way, this quantity that comes out, your book uses the letter beta for the decibel level. And this is important. Whereas intensity has units of watts per square meter, the decibel level is dimensionless, because when you plug in your intensity, you divide by the reference intensity, which has the same dimensions. So you're plugging a dimensionless number into the log function, and of course a dimensionless number comes out, and you scale by 10. So the decibel has no units. Let's go back and re-express all three of those intensities that we looked at in terms of the decibel scale. So what about the sound waves coming off of a person speaking a few feet away? We said that the intensity was around a milliwatt per square meter. So first, and I'm starting with step 2 because remember what I labeled step 1 was just choosing the reference intensity. First, we compare the intensity of this sound to our reference intensity. Now, you can just use the rule for powers, right? Subtract the bottom power from the top power. -3 minus -12 is +9. So the intensity of these sound waves is 1 billion times the reference intensity. Remember, the reference intensity is one that can, it's like the threshold of hearing. It can barely be heard by your typical person. This is a really large number, so we tame the large number by taking the logarithm. That's easy. Log base 10 of 1 billion is just 9. And now we're talking about a scale from like 1 to 10, let's say, or 1 to 12. Again, we'd like to have a little more resolution when we talk about the loudness of sound. So we scale that up by a factor of 10, and we call that 90 decibels. Okay, next example. And by the way, if you're wondering what's up with the capital B, I think it's because this unit takes its name from Alexander Graham Bell, the inventor of the telephone. Am I getting this right? So B for Bell. What about the rustling leaves? They were much quieter. First, we compare that intensity to the reference intensity, the threshold of hearing. We find that it's 100 times more intense. Just take the logarithm of that ratio, which is 2. And lastly, scale it up. So if we were discussing, or if we were rating sounds on a scale from 1 to 10 or 1 to 12, this sound would get a 2. But we'll scale everything up by a factor of 10, and we call that 20 decibels, which automatically tells us this is a much quieter sound than the 90 decibel person speaking. Last one. Oh, decibel level for a person standing right next to those giant speakers on stage at the Ted Nugent concert. Well, I'm going to change this 5 watts per square meter to 1 so that we can deal simply with powers of 10 here. Otherwise, I would actually have to use the calculator. So first we compare the intensity in question to our reference intensity, and we need to express, well, for convenience right now, if you have a calculator, you don't need to do it this way. But if I want to express this intensity as a power of 10, I recognize that 1 is 10 to the 0 power. So now, when we compare the two intensities, 0 minus negative 12, of course, is positive 12. That tells us that the sound waves hitting the eardrum of the person standing next to the stage at the Ted Nugent concert are 1 trillion times the intensity of the threshold of hearing, which sounds painful, right? Take the log of that number to tame the big number, and we'll just call it 12. Again, if we wanted to measure sound loudness on a scale from 1 to 12, we could just leave it at that, and this would be at the top end of the scale. But let's scale it up, and we'll call that 120 decibels. So a good number to memorize is once you pass 100 decibels, you're talking about sounds that are pretty loud. Now, I've been mentioning this as we go along, but let's take one more look. What would the decibel scale look like if we skipped the last step? So if all we did was just take the ratio, compared to the reference intensity, and then take the logarithm, if we stopped at that, what would the decibel scale look like? Well, you would just scale everything down by a factor of 10. So instead of 130 being the really loud end, you would just call it 13, 12 or 13. And you'll recognize that the number out front doesn't even have to be 10, right? I mean, you could stretch all the numbers out so that typical loudnesses ranged from 0 to 200. Really, it's like you're calibrating your scale by choosing that number out front. So why do we go with 10? I guess we just have, as people, we have an affinity for that number 10. We've got 10 fingers, most of us, 10 toes. We like that number. And it's probably also why the number is called the decibel scale. Although the deci could also be because we're using log-based 10. So maybe we just go with 10 out front to be consistent with the 10 in the base of the logarithm. Here's one more fact that's worth knowing. Every time you increase the loudness or the decibel level by 10 dBs, that corresponds to a sound that a person would perceive as being twice as loud. So if you just played a bunch of different sounds to somebody using a speaker system and ask them to describe in words how they compare, evidently people tend to agree on this. Once you've increased the sound by 10 decibels, most people will say it seems like it's around twice as loud. That's an imprecise measurement. Your perception and your ear are not a precise measuring device. But let's look at what that means mathematically. So if we've got two different sound levels, and the second one, beta 2, is 10 decibels greater than beta 1. I probably should have written dB here, 10 decibels. Well, we know that the decibel level is computed using this formula. Notice that for the second sound level, beta 2, I'm using the symbol I2 for the intensity, and for beta 1, I'm using the intensity I1. Well, there's another property of logarithms that we can invoke right now. Do you remember that the difference in two logarithms is is the logarithm of the quotient? Yeah. The sum of the logs is the log of the product. The difference in the logs is the log of the quotient. So if I factor out this 10 here, I can use the difference in those logs to form the to form the logarithm of their quotient. Let me say that one more time. I can use the difference of the logs to form the log of the quotient. So this quantity here is the numerator, and this quantity here is the denominator. And you'll see that the I naughts cancel. We've got one up top, one up bottom, or one down bottom, and we're left with this equation. Assuming this is true, that would imply that 10 times the log of the ratio of two intensities, where specifically this intensity is perceived as twice as loud as this one. Now, how do we continue with this equation? Well, we've got a 10 on both sides. The only way this works is if this quantity in front of the 10 is equal to 1, right? That would have to be equal to 1 in order to satisfy that equation. Well, just ask yourself, which number has a log base 10 that's equal to 1? What number has a log base 10 of 1? Wouldn't that just be 10? 10 to the first power is 10. The log base 10 of 10 is 1. I'm starting to confuse myself, but I think I said that correctly. All right, so that implies that the second intensity would have to be 10 times as great as the first intensity. This intensity in watts per square meter is a number 10 times I1's intensity. Okay, all that to say that, well, I guess there's really two facts here. Number one, if you increase a sound level by 10 decibels, it now, a person would now perceive it to be twice as loud. So we're not talking about the actual intensity, because you see down here, the other statement is the actual intensity is 10 times as loud. Okay, so multiplying the intensity of a sound wave by a factor of 10 corresponds to it sounding twice as loud. That's a little confusing. But so there's your other rule. Every time you increase the decibel level by 10, you're really talking about multiplying the intensity by 10. So as you go from 20 decibels to 30 decibels, that's 10 times the intensity. As you go from 30 decibels to 40 decibels, that's 10 times the intensity. And you can see now why going from 10 decibels to 120 decibels at a rock concert, that's a much more intense sound wave. And there's a very similar statement you can make for earthquakes. I remember learning that as a kid. You probably did as well. Going from like a 6.0 earthquake to a 7.0 earthquake means a big leap in the intensity of that seismic wave. So now that we've looked at how to convert from the SI units of intensity, that's watts per square meter, into the decibel level, can we do the opposite? Supposing we know the decibel level, can we then calculate its intensity in SI units? All we have to do is take the formula for beta in terms of the intensity I and flip it inside out, topsy-turvy it, solve for I. And you could probably figure this out in your head, just reverse the sequence of operations. So the last thing we did was multiply by 10. And that means to undo that, the first thing we'll do is divide by 10. And before that, we took the log base 10. To undo that, we would do the anti-log base 10. In other words, exponentiate with the base 10. And then the first thing we did was divide by I naught, which means to undo that, we would multiply by I naught. So here's what this formula says. It's everything I just said in words, but expressed mathematically. The first thing you would do is take beta and descale it by 10. Like if it was 90 decibels, divide by 10 to get back to 9 as the ratio, or as the log of the ratio of intensities. Then you do the anti-log, so you raise 10 to that power. And lastly, as I said, multiply by I naught. And after you've had some practice, you can actually do this very easily in your head for simple numbers. Basically, any number that's a multiple of 10, you can do this in your head. Let's use this example right here, 60 decibels. The first thing we would do is scale it back down to 6. We know that 6 is the logarithm of the ratio of intensities. So if the log base 10 is 6, just do the anti-log. 10 to the 6 is 1,000,000. That tells us that the intensity we're talking about is 1,000,000 times the reference intensity. That means 1,000,000 times 10 to the negative 12th. Let's do that in print. Take 60, descale it to get 6, raise 10 to the 6th power. That's 1,000,000 multiplied by the reference intensity. And there it is. That's a micro watt per square meter. Lastly, I dug up a couple tables from the web here to confirm one or two of the things that we already observed. Where's that rule about? Here we go. Every decibel level change of 10 corresponds to a perceived volume loudness of multiplication by 2, or in this case, multiplication by 1/2. So if you decrease the decibel level change, or excuse me, if you decrease the decibel level by 10 decibels, that volume is now perceived as half as loud. Up here, the table is confirming that the reference intensity of a trillionth of a watt per square meter, notice they left off the units there, it's implied SI units. That intensity does correspond to the threshold of hearing, how would you pronounce that? This is really gross. Look at the upper end here. We know that 120 decibels is typical of like a rock concert or some other kind of concert. By the time you get to 130, you're pushing the threshold of pain. You really don't want to be experiencing 140 decibels for any length of time at all. And then this is really bad news. Instant perforation of the eardrum. Yeah. What does that look like? Hey, what does that sound like, especially to the person experiencing it? I actually know somebody who had their eardrum perforated in an unfortunate moment where I think they were participating in, they were playing in a band. I think she was playing the trombone. She was sitting next to the drummer, and the drummer hit the bass pedal particularly loud. And because her ear was so close to the bass drum, you know, ill-advised, but she experienced a perforated eardrum. And I don't think she ever got that fixed. I don't know if you can fix that. Anyway, this is not for the faint of heart, but if you want, I have a picture here of a perforated eardrum. Just kidding. I wouldn't do that to you. Cheers.